Hi, welcome back. Today will be probably the most important video on this channel. If you are a Masters of AI student or perhaps even in undergrad, well, we're talking about the idea of informed search, moving towards heuristic search, and we're going to be going over the famous Astar algorithm, which remains state-of-the-art and is extremely fundamental in a lot of the AI technologies and applications in the world around you, even today. This is essentially Astar in a nutshell. So to get started, in the previous video, we've just had a look at the basic search strategies, right? So things like BFS, DFS, UCS, DFID. So these search strategies essentially are the foundational stepping stones towards these algorithms, but we're going to be talking about they all have one large fatal flaw. So all of these, I guess I'll discuss this from the UCS perspective. UCS kind of emerged as the better version of BFS. It works for problems with costs, which is kind of where we're moving towards, right? Even in a standard grid map, if you have a diagonal, well, the diagonal is probably a smaller cost than your straights, right? So real problems usually have different costs. We would be using uniform cost search. However, these algorithms are all what we're going to be calling uninformed. They have a fatal flaw, which we're going to essentially shore up using the Astar algorithm to dramatically improve upon the practical performance of these algorithms. Now, I'll put up the graphic over here, but what's really interesting about these algorithms is essentially they're conducting search in this radial pattern outwards, okay? So we are expanding by G, we're expanding by the cost so far. So that means essentially, right, you're treating all directions as equally promising, right? However, of course, this is pretty dumb, right? As human beings, say I dropped you into a search problem and essentially there is a target, there is a massive flag, right? Pointing out your exit. You know where the exit is. Well, I think intuitively, of course, you're not going to expand in all directions equally, right? You, as a human being, identify, I can see the goal, I know the direction that the goal is in, and that means, of course, you're going to put more emphasis, more preference on following promising paths that hopefully look like they're, right, taking you towards the goal, okay? So this is what we call, essentially, this is problem-specific knowledge, okay? You're given a problem with a start and a target location. Well, we know as human beings that we want to use the additional information about where the target is to help inform search. This is going to be what's called an informed search algorithm. So we're tracking now two things. Instead of when we're going from some start node S to a target T, we've already conducted some amount of search, right, to some node N. Well, we have previously, it's just the cost so far. How many steps, what was the cost to actually reach this node? Well, then we also now have this idea that we will try to estimate how far away we think we are from the target. This is an estimate of the distance to go, okay? So the search strategy for Astar really is as simple as it's going to leverage the advantages of both sides of this, right? So we have the advantage of knowing how far we've come, right? How much work we've done to get here. And then we have the concept as well of estimating how far away we are from the goal, from where we want to be. We put this together into an evaluation function. It is simply just f of n is equal to g of n plus h of n. F equals g plus h. The Astar algorithm is that simple. I won't talk about it in this video, but it is actually provably an optimally efficient search strategy. Ranking nodes by this, up until tie breaking, is the best strategy we can come up with. And so that's quite exciting. There are ways to improve upon the Astar by doing additional reasoning to prune things from the search space and so forth. So know that Astar is routinely improved in the literature and in state-of-the-art algorithms, but it is essentially built upon, right? The search strategy here is extremely exciting. Now, to define that, of course, I wrote it below. G of n is our cost so far. H of n is now what we're going to be calling this estimate of the distance to go. We're going to be calling these heuristics, okay? So heuristics are just essentially rule of thumbs. They are some function we can come up with by essentially reasoning over the world, coming up with pattern recognition or reframing of problems. We're using human intuition and human pattern recognition to essentially come up with a function to give us an estimate of how far we need to go. So in some problems, right, like in a Rubik's Cube, it's pretty hard even for us to know how many spins you need to solve the problem. So we always have to come up with simplifications for the world. The standard ones you usually see is the Manhattan distance, octile distance. Well, this is just in a grid. It's essentially the greedy estimate of hey, if there were no walls, just how many steps, how many grid cells away am I from the goal? So heuristics are really exciting. There's a whole field of study there. Again, we're not going to go into depth in that in this video. However, there are two important characteristics that heuristics need to satisfy in order for the Astar algorithm to even be called Astar. So traditionally it would be algorithm A, right? Algorithm A is just f equals g plus h. Algorithm A star, which is really the only one that's ever used, this is the case when we have a heuristic that satisfies two criteria. One, that it is admissible, and two, that it is consistent, okay? These, I think, are the things that scare students the most. They're relatively simple, so let's dive into them. So admissibility really is the easy one. This is just saying that in our estimates, right, we can never, ever, ever overestimate, okay? When I'm trying to return a distance of how far away I think I am, I have to make sure that it is either equal to, in an ideal sense, we get the exact distance, that's great, that's the most informed, right? We're getting the most information, but otherwise it has to be lower, okay? It has to be overly eager. In the case that it returns, if the true distance was 10, we return anything higher than 10, even 11, our algorithms can break. We'll have to encounter these issues of re-expansions. That is not something we're dealing with here in this video, but admissibility is really, really important. You have to make sure that your heuristics are optimistic, okay? Mathematically, that's just the same as saying our heuristic estimate from some node n, right? Well, this has to be less than or equal to. It cannot overestimate. The true distance we represent as c star of n, right? You're just saying from node n, the true cost, the true distance c star, well, our estimate has to be less than or equal to that. Finally, so next then, there is the idea of consistency. This one I think is substantially harder for students. I think, especially if you don't have much background in mathematics, well, this one can be a little bit weird, especially if you haven't seen many proofs with the triangle inequality. I think consistency though is a lot easier than I think we make it out to be. But you might just have to kind of have a look at it yourself and deal with, like, when we look at the example problem over here, like how heuristics maybe correspond to this. Consistency really is just saying our estimates monotonically decrease from n to t. Okay, so admissibility is kind of like this global viewpoint, right? From any node all the way to the end, it has to be an underestimate. Consistency is like this local reasoning, right? So for any triangle we can draw between neighbors, essentially, between local steps. Well, what we're looking for, when we say it monotonically decreases, we need essentially our function to be consistent. It has to either stay the same, right, which is not very informative, but that's fine, or decrease. Monotonically decrease means only ever stay the same or decrease. So that can be a step function, or it could be smooth. It doesn't matter. We just need to make sure that it is consistent, meaning that it is not jumping around, right? If you take one step closer to the goal, and your heuristic previously said 10, and all of a sudden it jumps up to 20, right? This idea of like a non-smooth, this random kind of heuristic, well, that is not consistent. So essentially this is just saying that our heuristic, our estimates, right, it has to essentially only ever decrease towards the goal. It only ever points us in the right direction. So if you have a heuristic that randomly spikes and jumps and has these random dips and upward trajectories, well, that is not consistent, right? It can only ever stay the same or decrease. Okay, so mathematically, this is all stemming from the diagram here, which I'll write up as the equation as well. What we're saying, we're reasoning over us being at some node n, right? And then we are actually taking a step from n to one of its successors, right? One of its neighbors, which is going to be called n prime here, okay? So when we take this step, well, we're now reasoning over how our heuristic estimates from both of these nodes relate to each other. For it to be consistent, essentially what we're saying is just that the triangle inequality has to hold, right? The values are going to be monotonically decreasing. The triangle inequality really just says that essentially one of the sides is essentially less than or equal to the sum of the other two sides. We write that up here mathematically, just saying that our heuristic estimate from node n, right, in order for it to be consistent, it has to be less than or equal to the actual cost of the step we took, plus the new heuristic value. So in the case that things align nicely, we have this monotonic function, well, that means that our heuristic estimates are going to be informed, they're leading us in the right direction, we don't encounter all these issues of random jumps, and the triangle inequality holds. The key idea there is that consistency actually implies admissibility. So if you find a heuristic that is consistent, then it will also be admissible. So I view these as like global reasoning, and then this is the stronger version of it, right? If it holds consistently in all your local regions, well then it also will be true at this global scale. Now, now I think this is the hardest part of Astar. This takes a while to get used to. I have videos where we walk over examples of common heuristics and how they relate to admissibility and consistency in different kind of domains, so I highly suggest that video here. Okay, otherwise, let's jump over here then, and the last thing I want to do is walk through a very quick traversal example of how we're actually going to operate Astar. I've drawn up the H values here for each node, and then we also have the edge costs. So that's our G as we progress. Okay, so I've essentially just labeled two of the nodes here as the start location. So we're starting at node B, we're dropped in at B, and then we're trying to find our way to the target location at node H, okay? At location H in our graph. We are going to be walking through an example of how Astar works. So Astar is going to maintain two data structures. First is the open list, which is a priority queue, where we're going to rank nodes by F equals G plus H. Essentially, the open list corresponds to our frontier. These are the nodes we've now generated, we've encountered, but we have not yet expanded. Well, in terms of that graph search conversation, we also include the closed list to also remember to track the nodes we've already seen, which helps us with the idea of duplicate detection, okay? So when we expand a node, it gets removed from open, popped from open, and it will be placed in closed. Okay, so let's have a look at the example. So obviously at the beginning we're going to be expanding the root node, our start location B. We are at location B. Obviously our G is 0 because we haven't yet taken a step, which means our F is just going to be the heuristic value of 4, okay? So what we'll actually see as we progress search, F values will only ever increase, right? So this is kind of like our optimistic estimate. We think we can get there in 4 steps. Now, as you discover more detours that we have to essentially prove that we're going to have to take a longer route, well, your F value will be slightly pushed up. It will sometimes stay exactly the same, right, if you keep stepping happily, but it will never decrease, okay? Part of this is that anytime we ever expand any node during Astar, well, we're actually guaranteed that it is the optimal cost to that node. So actually, when you expand a node with Astar, you're actually guaranteed that is the optimal cost to that node for any node during search. That means, and that's quite exciting, but that's also why essentially we get this idea that when we expand the goal, well, obviously we're done and we have the optimal cost. So let's continue. So of course the first thing we do then is that we expand B to generate its children, generate its successors, the places we can reach from this location. So from B we now find both A and C. Remember, this is a priority queue, so they're both ranked by their F values. C has a cost of 2 to reach it, plus 4.5, so C is 6.5, and then A is ranked lower. A is ranked with 8, right? 3 plus 5. Okay, so we begin. C is looking the most promising now. Oh, note as well, actually, we just expanded B, so what happens? B is placed with its cost into the closed list. Why is this useful? Again, whenever we encounter any nodes, we'll see in a second, we can prune them based on already having seen it. And also, as I just said, knowing that we just expanded the node, well, it must have been the optimal cost, right? We can't improve ever getting to B in any other way, so B will never be important again. So what we do next is we expand node C, okay? So this is where I was getting at. From node C, we can reach 2 nodes, right? We can reach node D, but we can also go backwards to node B. In tree search, the naive version, well, we would also just generate B and have to search over that again. But because we're doing graph search, Astar uses graph search, we maintain the closed list. Well, ta-da, we've already seen B. So we get to throw that away completely. We don't need to generate that. We just generate the new nodes that we have not yet seen before. Well, that is D, okay? So D is added to our open list with a cost of, remember, G is the cost so far. It's not just the cost of the current edge we're traversing. The cost so far is 2 plus 2, right? So G is 4 plus our value, our heuristic value, so that is 6.8, okay? Which still looks more promising than A. Okay, what we're going to do then is we expand, and remember C goes into our closed list. Okay, now we expand D, so we're going to put this in the closed list as well. With D, well, we now encounter again C, but we've already seen C. So what we do is we add in E. So E is added in with a cost of what? Well, 2 plus 2 plus 2 plus its heuristic value of 2. Okay, interesting. So we now have 2 nodes that are ranked the exact same. This is where we say Astar is optimal up until tie breaking. So it is your choice. You get to choose which one you expand first. It will impact, I guess, the performance of your algorithm, but we still maintain our completeness and our optimality based on these heuristic characteristics, regardless of which one we expand first. So we rank things, the search strategy itself is rank them by F. If it's the same F, you're going to have to tie break in some regard. Coming up with that was hard, but usually in Astar we tie break by having gone further first, right? You essentially tie break by which one is closest to the goal, so the smallest heuristic value. Well, in that case, I mean, A has a heuristic value of 5, E is 2. So search thinks E probably looks closer, so we're going to just deal with that example. We expand E, we generate its neighbor now, which is F. F is added in with, so 2, 4, 6, 8, 10.8. What that means is F is going to go at the back, right? So A with 8 goes first, then F with 10.8. Okay, so then what that means is that we're going to expand A first this time. I think I forgot to put E in the closed, so E with 8, and now we add in A with 8 as well. So we now, from A, we discovered 2 nodes. We discovered node H and we discovered node I. Well, H has a cost of 8 plus its heuristic value. So H is added in with 8. Now, its heuristic value is 0. That makes sense, I forgot to say. An important aspect of your heuristics, right, is that the heuristic value at the goal is 0, yeah? The number of steps from the goal to the goal is, of course, 0. We want our heuristics to lead us to the goals. So H is added in with 8. I is added in with the cost of 3 plus 4, so 7 plus 3 is 10. So I looks like 10. F is still 10.8 at the end. Is that off the edge? Yeah, so F is 10.8. Okay, so then finally we have that H is the most promising. We are going to expand H. Well, H was the goal. When you expand the goal, essentially you have a goal test, right? Every time you expand a node. Ta-da, we now know that we're done. So we have found the goal. Essentially, when you expand a node, again, you're guaranteed that it is the optimal cost to that node. Well, the cost so far was this path here, which had a cost of 8. We have found the goal with a cost of H. We get to be done. So this is the Astar algorithm. It's extremely fundamental, very important in the field of AI. It's a driving technology behind a lot of exciting algorithms and applications. So please join me as we continue on future videos to expand upon the Astar algorithm and to essentially lead us towards current state-of-the-art in the area. But Astar is, and always will be, the most common algorithm that we all must know and learn. So thank you for watching and see you soon.